and the differential cross section. So first, you know that when we define that differential cross section. So you know that in the scattering experiment that this is the incident plane wave or particle incident beam, which we represent with the incident plane wave. When it collide with or interact with the scattering particle, that will get scattered through or that will diverge in all direction. And we define the differential cross section uh, that the number of particles scattered into an element of solid angle d omega in the direction of theta phi per unit time and incident flux. So here we define this is the mathematically for the differential cross section, where this is j incidence is the incident flux, and then theta phi is function of theta phi is representing number of particles scattered into an element of solid angle d omega. So this we earlier we have discussed regarding. So now in order to drive the relation, we know that this is the expression for differential uh, cross section. And so here we have to define J incidence, this is incidence flux, and expression for this and expression for this dn by d omega. So first we will drive the write the expression for this dn. What is the dn? Dn is the number of particles scattered into an element of d omega in the direction of theta phi per unit time. Uh, uh, and in this area element dA, and dA we define this is r square d omega. This is the area element, the particles. So the expression for this dn we can write this is the scattered flux into the area dA, and we write this in term of the solid angle. And on rearranging this we can write dn by d omega, which is equal to j scattered flux into r square. And we know that now this quantity in this differential cross section is equivalent to this. So it means that in order to determine this quantity, we have to determine this j scattered, the flux scattered density. So in order to scattered flux density, the expression is we write this iota h cross by 2 mu, and this is representing the mass, and this is the phi uh, this sc represent the scattering. So this quantity is representing the scattered wave function, scattered wave function related to the scattered particle. So, and this is the gradient of the scattered function, but it is the complex conjugate of this scattered function, wave function. This is minus complex conjugate of scattered wave function is into gradient of the scattered wave function. And you know that this scattered wave function, we in the earlier lecture we define this wave function by this quantity. A is normalization factor, and f of theta is thus we call it scattering amplitude, and this is representing the EIK R. This is representing the wave which is moving uh, radially outward direction, which is moving in this outward direction, which we denote with this quantity E exponential iota kr. So this is the scattered wave function. So here we have to now, our objective is to solve it, to solve this. And we know that this is, we have to find here, this is gradient of this scattered wave function, our complex conjugate. So we have to determine this and this quantity and multiply with the scattered wave function. So first, and this is scattered wave complex part. I will take minus iota kr, and first I will find this gradient of phi scattering scattering wave function. So this, if we take the gradient of this, so a and this d theta, that is not depend upon the r. So here this is function. I can write this is u and v, the formula which we use in differentiation. So the differentiation of this iota kr comes out to iota k this is, and write in denominator this r as it is into this iota k iota kr, and minus uh, same function as, and derivative of this r. So derivative of r is 1 here. So we on so we get this type of uh, these term on now, because in here in here we have to multiply with this quantity in order to find this. I have to multiply scattered wave function. So if I multiply this with this quantity, so here you have iota kr. So iota kr here is negative, so exponential terms will get cancelled, and we get here a square f of theta ka modulus whole square, and iota k by r square minus 1 by r cube. So we will get this is the value of this term, and similarly for the second term we will take the gradient, and this is gradient of scattered wave function. So we will get this type of expression, f of a f of theta iota kr exponential iota kr minus iota kr. This is the simple differentiation, and we will get small multiplying we to get a square, and this we got the same term, only difference is within in this minus sign. So on substituting the value of this and this term in this expression, on substituting here in this, say for example this equation number 3, so on substituting here 3, we get the value of scattered flux. This is k, and iota kr I will substitute here minus iota kr minus 1 by r minus iota kr square, minus minus comes out to plus. So here these two terms, they will get cancelled with one another, and we left with a minus 2 iota k r square. So with the 2, this 2 will get cancelled, and we left with h cross k mu r square a square into f of theta scattering amplitude whole square. Okay, so we got this is the value of scattered wave flux. So now this is we have uh, determined this quantity, and now we can substitute here in this equation. If I substitute the value of this j s here, so the value of this equation, if I substituting the value of this r square into this is the value of j s, this value on substituting here we will get r square, r will get cancelled here. So basically this is the value of, we got this parameter now. Now similarly now we left with one term, this is incident flux. So we will use in, we will solve in similar fashion. J incidence, the flux density J incidence, we write in similar fashion iota h cross 2 mu bracket phi incidence wave function for incident plane wave, gradient of phi incident complex function of incident wave minus complex conjugate of incident function into gradient of incident uh, wave function. Okay, and we write here this is k naught for incident wave, we represent this wave vector k naught. Okay, so on substituting, putting using this wave function in this relation, we got the value of j incidence, which is equal to h cross k naught by mu naught into a square. So we got this expression. So in order to solve the this differential cross section relation, we can have the, we have evaluated the this both relation j incidence flux and this dn by d omega. So on substituting these quantity in this differential cross-section relation. On substituting these values, we got here k by k naught into f of theta ka whole square. So here you can see that this is the differential cross-section and this is scattering amplitude. So this is representing that this relation differential scattering uh, cross-section is independent of a normalization factor. It doesn't depend on the k is wave vector for scattered wave function, a scattered wave, and this is wave vector related to the incident wave. So for example, if now I will consider the another case that y, for example, elastic illusion, and for example here it is not depend upon a, so we can consider a to be unity. You can take a to be unity. It doesn't depend on this. Okay, so now for example consider that the scattering process which is taking place collision is the process is elastic. In that case elastic process we will consider that this is k naught comes out to be k. So wave vector incident uh, wave vector, and this is scattered wave function, scattered wave vector. This is basically representing the wave vectors, okay, for incident and scattered. Okay, so if they are equal for elastic scattering, so on substituting here, because k is equal to k naught, then this quantity comes out to be unity. And if it is unity, then we can say this is the differential scattering, differential cross section is directly proportional to the, or is equal to the square of the scattering amplitude. So this is about the relation which is true for the elastic scattering. So this is all about the relation.